Welcome back to the deep dive. If you've ever felt like cloud architecture is just this sprawling metropolis of interconnected invisible wires, you are definitely not alone. Today, we're taking on one of the most fundamental and, let's be honest, often complex journeys, decoding cloud networking.
It really is. It's the scaffolding for everything else you build. I mean, people love to jump to their applications, their databases, their shiny new microservices. But if you don't really grasp the foundational networking concepts, how traffic is routed, how it's secured and isolated, you're basically building these amazing complex solutions on a structure you just fundamentally don't understand.
That feeling of being lost in the invisible infrastructure is exactly what we're here to eliminate. For a lot of you listening, this is probably your first serious foray into this layer of technical architecture. We know the jargon can get pretty dense, so our mission today is simple. We are giving you the foundational map. We've gone through a stack of essential and intermediate technical scenarios to really distill the core concepts into clear, understandable insights. We're focusing on the absolute building blocks, isolation, which is your VPC, security.
Just like NAT and Cloud Armor.
Yeah, exactly. And then external traffic control and, of course, hybrid connectivity.
And we're going to be focusing on the why. Why choose one solution over another? Why does this one specific configuration detail actually matter? We'll use some clear, consistent analogies that should really stick with you. So when you walk away from this deep dive, you won't just have a list of definitions. You'll have the context you need to start tackling even those intermediate architectural challenges with some real confidence.
Okay, let's do it. Let's unpack this and start at the very beginning. If we're building anything at all in the cloud, we have to start with our own private space.
Which brings us to the essential starting point. The virtual private cloud, or VPC.
Right, the VPC. It sounds like a total buzzword, virtual private cloud. But what does that actually translate to in practical terms for you listening at home?
Yeah, let's stick with that city analogy we started with. If the entire cloud provider's infrastructure is a massive public city, a huge grid of roads, utilities, public spaces, the VPC is your private, isolated, software-defined network space within that city.
Okay.
Think of it like you've purchased a large private piece of land and you've erected your own secure building on it. And crucially, it's logically isolated from every other customer's VPC. So even though the underlying physical hardware is shared somewhere down the line, your network pathways and your addressing are completely private to you.
So it gives you the legal boundaries and the building structure, making sure nobody else can just wander into your network address space unless you explicitly let them. That isolation, that's the core feature then.
Absolutely. And inside that massive structure, your VPC, you need to divide the space logically. That's where subnets and regions come in. See, VPCs are global in scope. You define a VPC once, and it exists across all these geographical regions worldwide. But the subnets you create within that VPC, those are like the individual rooms or floors, and they're tied to specific regions and availability zones.
Why is that distinction so important? Why can't I just have one giant subnet that spans, say, the US and Europe?
Because subnets are where the actual compute resources live. Your virtual machines, your databases, your managed services, they all reside in a subnet. And to make sure you have low latency and good resilience, those resources have to be rooted in a specific physical location. So while the VPC gives you that worldwide blueprint, the subnet is the specific localized address where your machine actually lives. If you need a presence in two different regions, you have to define two separate subnets within your single global VPC.
I see. So that regional boundary prevents resources in one region from just automatically being available in another, which helps you manage things like latency and, I guess, failure domains?
Precisely. The VPC is the big organizational umbrella. The subnets are the geographical rooms.
Okay, that's a great clarification. So now we have our building, we have our rooms. The real complexity starts now, right? Controlling who gets to talk to whom inside the building. We need that internal security.
And that leads us directly to controlling internal traffic flow with firewall rules and tags.
Let's use that classic scenario, the three-tier application. You've got your web tier, your API tier, and your database tier. They're all inside my secure VPC, maybe even in the same subnet. But if a breach happens at the web tier, I absolutely do not want an attacker to be able to jump directly to my database. I need strict east-west traffic control. That's the movement between my internal resources.
Exactly. The goal is microsegmentation. In the pre-cloud world, you would have done this with static IP addresses. You'd list out the exact IP of the API server and then write a rule saying only that IP can reach the database server's internal IP on, say, port 3306.
But in the cloud, especially with modern auto-scaling applications, that is a complete nightmare. IPs are ephemeral, a machine scales down, an instance restarts, and suddenly your security rule is pointing at an IP that doesn't exist anymore, or worse, has been repurposed.
It's not just a nightmare. It's architecturally unworkable for any application that's designed for elasticity. We need a system that labels the function of the machine, not its temporary network location.
Yeah.
And that is the power of network tags.
So the solution is to abstract the identity away from the address itself.
Yes. Network tags are just metadata simple strings like web front end or deep replica that you attach to your compute engine instances,
Right.
your VMs. Then VPC firewall rules let you define traffic flow using these tags. We can go back to our security uniform analogy for this one.
Okay.
You create a rule that says anyone wearing the API uniform is allowed to speak to anyone wearing the database uniform on the required port.
And that makes the whole system incredibly dynamic. I can set that rule once, and if my API tier auto-scales from 2 instances to 20, every single new instance is instantly recognized and secured by that tag rule, because they all put on the API uniform as soon as they're created.
That's it. It allows for true independence and scalability in your application tiers.
That independence has to be the primary benefit. It's what lets DevOps teams move fast without having to constantly call up the networking team every time a single instance is provisioned or decommissioned.
The security policy is enforced at the tag level, completely detached from the underlying dynamic IP assignment. It just works.
Now, when we start talking about having multiple security rules that allow some things and deny others, we're going to run into conflicts. That brings us to the critical concept of firewall rule priority. If 2 rules could apply to the same packet, how do we know which one actually wins?
This is a detail that trips up everyone, experienced users and new users alike. And if you get it wrong, you either end up with blocked production traffic or, wide open security holes. The fundamental rule is this. The rule with the lower priority number wins. Priority 0 is the highest priority, and the numbers go up from there, like 100, 500, 1,000. The firewall processes rules in ascending order and just stops at the first one that matches.
So a lower number means it gets enforced first, a higher priority. Our sources had a really specific intermediate scenario that highlights this. How do you allow specific Active Directory traffic into a super restricted subnet but deny absolutely everything else coming in?
Right, you have to use that priority system to create an exception to a general denial. So, to solve that, you define 2 rules. First, the specific allow rule. This allows the specific ports and protocols you need for AD traffic, like LDAPI or Kerberos. You give this a low priority number, something like 100.
Okay, that's the exception.
Exactly. Then you have the general deny rule. This is a broad rule that just denies all ingress traffic. You give this a high priority number like 1,000.
So if a packet comes in and it's that AD traffic, it hits rule 100 first, it's allowed through, and the firewall just stops processing right there. The deny rule at priority 1,000 is never even looked at for that packet.
Correct. But here's the common mistake. If you accidentally assign that deny all rule a priority of 50,
which is a lower number, so a higher priority.
Right. The firewall hits that deny rule first, blocks all the traffic, and your necessary AD connectivity just fails silently. Understanding that priority order is absolutely non-negotiable for effective troubleshooting and segmentation.
And speaking of troubleshooting, how do we even confirm if these rules are being hit and applied correctly? Because if a rule is denying traffic, the instance just sees a timeout, right? It doesn't tell the user which rule was the problem.
That's the next essential step in mastering this. Troubleshooting security requires visibility. By default, firewall rules are silent. To evaluate the effectiveness, the efficiency, the utilization of your rule set to see if that priority 100 rule is being hit 10,000 times a day or maybe never, you have to explicitly enable firewall rules logging.
And that's a specific toggle, right? It's distinct from just general VPC flow logging.
Absolutely. VPC flow logs track the metadata of traffic that's passing between instances, source IP, destination IP, the volume of data. Firewall rules logging tracks whether a specific security policy was triggered. Did this packet hit the deny 1,000 rule, or did it successfully pass the allow 100 rule? If you're trying to debug connectivity or just confirm your security posture, enabling this logging is vital. Without it, you are truly just guessing about the actual behavior of your security boundary.
That depth is incredibly useful. Okay, we've covered isolation and internal security for a single application. Now let's zoom out to the enterprise level, where you might have dozens of different development teams, hundreds of projects. This introduces the challenge of securing governance.
Yes, shared VPC and IAM. Governance in a large organization is a complete nightmare if every single application team owns and manages its own network infrastructure. You just end up with overlapping IP ranges, inconsistent firewall policies, and dozens of people who suddenly have permissions to open up holes in your network.
The main pain point here is that requirement to separate duties. The networking team needs to control the boundaries, but they shouldn't need access to the application data. And on the flip side, the application teams need flexibility, but they shouldn't have the power to, break the company's network security rules.
That separation is the exact use case for the shared VPC architecture. This pattern enforces centralized control over the network while maintaining decentralized control over the compute resources and the data itself.
How does that architecture physically divide up the responsibility?
You designate one project as the host project. This is the domain of the networking team. They centralize all the critical infrastructure management, subnet creation, IP addressing schemes, routing tables, and the master set of firewall rules. They get assigned the appropriate network admin roles in this project.
Okay, so the host project is the kingdom of the network admins. What about the application teams?
Their projects become the service projects. The service projects are attached to the host project's network. So the developers, they launch their compute engine instances within their own service project, but those instances are actually leveraging the network configuration that was defined by the networking team back in the host project.
The genius of this separation is that the developers who have the compute admin role in their own service project can manage their application code, their data, their VM lifecycle, but they explicitly lack the permissions to modify the fundamental network infrastructure. They can't change a firewall rule or delete a subnet.
Exactly. The benefit is crystal clear. Security compliance is guaranteed because the policy is centrally managed. The networking team manages the roads and the borders, and the development team manages what's loaded into the application. It creates this necessary, non-overlapping separation of duties, which is foundational for enterprise security and for any kind of auditing. This architectural choice is often mandated by regulatory requirements, not just technical preference.
Okay, that wraps up our private cloud foundation. We've built our isolated structure, we secured the internal flow, but as we move into Section 2, we have to acknowledge that even the most private server eventually needs to talk to the public internet, even if it's just to check for a security update or grab a package from a public repository.
You can't run modern infrastructure in a complete vacuum. Systems need maintenance. This leads us to addressing private instances where we have to solve that problem of requiring one-way, outbound-only access.
Right. So the problem is simple. My instance is in a private subnet, meaning it has no external IP address. Great for security. But now it can't get to securityupdates.com. If I give it an external IP, I defeat the whole purpose and expose it to inbound attacks from the internet.
The recommended and most secure solution here is Cloud NAT, or Network Address Translation. It's designed specifically to allow your private instances to initiate an outbound connection to the internet to go out and get those security updates and then receive the response back. Crucially, it blocks any external entity from starting a connection inbound to that private instance. It's truly a one-way ticket, and it can only be initiated from the inside.
Let's really elaborate on the analogy for this, because I think this is a concept that can confuse first-time network architects. What exactly is the Cloud NAT gateway doing?
Okay, think of Cloud NAT as the secured communal mailroom for that large private residential complex we were talking about earlier. All the residents, your private instances, have internal addresses, and they're inaccessible from the street.
I'm with you.
Now, if a resident needs to send a letter, initiate an outbound connection, they drop it at the mailroom. The mailroom then attaches its own public return address, the NAT IP, and sends it out.
So when the update server replies, it sends the response back to the communal mailroom's address, not the private instance's internal IP.
Exactly. The mailroom, the NAT, then securely routes that response package back to the correct private resident who started the request in the first place. An external attacker who's trying to initiate contact can only address the communal NAT IP. They can't ring the doorbell of the individual private instance. This guarantees security while still ensuring functionality.
Our sources were really clear on the application here. If your instances are in a private subnet and they need access to public repositories for package downloads or software dependencies, configuring Cloud NAT for that specific subnet is the definitive secure requirement.
It is the standard solution for securely managing egress traffic. And it's also worth noting that in a more sophisticated architecture, you can configure NAT to only apply to specific subnets, or even control which IPs it uses for outbound traffic. It adds another layer of flexibility and auditability.
Okay, we've secured our internal machines that talk privately to the internet. Now let's pivot to the machines that must be public-facing, like an e-commerce platform. Those are the ones under constant malicious attack.
And that takes us to protecting the public edge with Cloud Armor. Public-facing services, especially those exposed via load balancers, are targets for everything. Volumetric distributed denial of service, or DDoS, attacks. Highly specific application layer attacks like SQL injection or cross-site scripting.
And without protection, those malicious requests just consume your application resources, they slow down legitimate customers, and ultimately they drive up your compute costs and risk a data breach.
Cloud Armor is the global edge security solution that provides that necessary layer of defense. It works as a web application firewall, a WAF, and a DDoS mitigation service, and it stops these threats before they even hit your application servers. The massive advantage here is that because it operates at the global edge of the cloud provider's network, it requires zero code changes to your backend application.
That is a huge operational benefit. You don't need to modify your application stack just to bolt on some security features. But where do I attach this powerful shield?
Deployment is key here. Cloud Armor works by attaching policy rules to a global HTTPS load balancer. Since the load balancer is the global entry point for all public HTTP traffic to your cloud environment, attaching Cloud Armor there means every single packet is inspected before it reaches your backend services.
It doesn't matter if those services are VMs, managed instances, or GKE containers. It's the bouncer standing at the most critical front door, filtering based on things like geolocation, IP reputation, and specific threat signatures. So if a load balancer is the essential ingress point, Cloud Armor is the necessary security layer that sits right behind it, shielding the entire back-end application layer.
It provides the first and most crucial layer of public defense.
Now let's talk about enforcing security not just in one project, but across an entire corporate structure. We're moving from local rules to organizational mandates with restricting public IP use via organization policy. Why would a company want to globally prohibit developers from assigning public IPs?
It all comes down to risk minimization and eliminating unauthorized attack surface. If developers have the freedom to assign external IP addresses, you end up with rogue instances. Maybe a test server that was left exposed with bad security, or a VM with highly sensitive data that can now be reached directly from the internet. Organizations want all external access funneled through controlled points, like load balancers that are secured by Cloud Armor.
So the goal is to make private the default and public the exception, which is rigorously managed by the network team. But in a large organization with hundreds of development teams, manually checking every single new VM deployment is just impossible. We need enforcement at the highest level.
And that's where the power of organization policy comes in. This is not a firewall rule. It's not an IAM permission. It's a global constraint that's applied at the organization level, above all the projects and folders. The specific constraint you use to enforce this is constraints compute.vm external access. By setting this policy, you enforce the requirement that external IP addresses can only be attached to approved instances across every single project and every single VPC under your corporate umbrella.
I see the distinction. A VPC firewall manages traffic flow within a network. An organization policy manages the creation of resources. It puts a security guardrail around architectural choices. It's the global, non-negotiable zoning law that dictates the basic building rules.
It prevents configuration drift, and it ensures enterprise-wide security compliance, leveraging automation to enforce best practices at scale.
Okay, as our applications leave that secure boundary and start dealing with global users, the next big challenge is managing massive volumes of external traffic efficiently. This requires sophisticated load balancing, and we really need to clarify the fundamental differences in how these load balancers operate.
We absolutely have to. We must differentiate between Layer 7 and Layer 4 load balancing because they serve completely different needs. Global traffic steering with L7 load balancing is all about application intelligence.
So if I'm building a highly available, globally distributed application, think a major e-commerce site, I need my traffic controller to be smart. I need it to understand the request itself, not just the network packet.
And that level of intelligence requires the HTTPS load balancer with URL maps. This is the standard best practice for L7, or application layer, routing. It operates globally, so it provides a single IP entry point for all your users worldwide, and crucially, it handles the SSL/TLS termination, which ensures end-to-end encryption to meet security standards.
And the intelligence, the steering that comes from the URL map.
The URL map is the configuration component that lets the load balancer inspect the path of the incoming URL request and then route it to a specific backend service. For instance, you can route example.com inventor resume to the inventory service backend and example.com images to a completely separate content service. This is often the mechanism used by modern Kubernetes or GKE deployments via something called an ingress resource. It lets you expose multiple microservices under one public IP and then apply policies like Cloud Armor to that entire entry point.
It's the traffic cop that looks at the address on the envelope and directs the car to the right office building based on the department name. That's L7 smart routing, global reach, and application aware.
And that covers most web traffic, but as you alluded to, not all traffic is web traffic.
Exactly. Low latency traffic with L4 load balancing introduces a totally different set of constraints. What if my service is a real-time gaming server or a high-frequency trading data stream? They often rely on different protocols like UDP, and latency has to be minimized at all costs.
For these specialized needs, L7 is often too slow, or it introduces undesirable side effects. These services demand two key things: extremely low latency and preserving the client's original source IP address.
Okay, why does L7 obscure the source IP, and why is that such a problem for gaming or real-time communication?
Well, an L7 load balancer typically acts as a proxy. It terminates the connection from the client, reads the payload, the HTTP request, and then it initiates a new connection to the backend server. So when the packet arrives at your backend, the source IP address is the address of the load balancer, not the original client. For protocols like UDP or applications that rely on the client IP for licensing or geolocation, that's fatal.
So we need a dumber, faster load balancer that just gets the packet where it needs to go without interpreting the content.
We use the external TCP UDP network load balancer, often called a pass-through load balancer. This is a layer 4 load balancer, meaning it only looks at the IP and port header, not the application content. The term pass-through is crucial. It does not terminate the connection. It simply routes the client packet directly to the appropriate backend VM.
And that operation ensures low latency because it's not wasting time inspecting the application layer, and it preserves the source IP because the connection isn't terminated and re-originated.
It's the go-to solution when you need pure, unadulterated network performance and that source IP fidelity. It's also worth noting that because of its low-level operation, it's typically regional, not global, so it focuses performance in a specific geographic area.
So L7 for global application intelligence, L4 for regional speed and source IP preservation, a really critical distinction for any architect.
Now let's combine that traffic management with content delivery to really minimize that global latency. That brings us to the content distribution network, or CDN, strategy.
Right. If I have users all over the world accessing large assets, images, videos, software downloads, the speed of light means that distance introduces lag. I need a strategy to get the content physically closer to the user.
And that's the global warehouse analogy. Your origin server is this central factory. If everyone in the world has to wait for a shipment from that central factory, delivery is going to be slow. A CDN strategically stores copies of your content inventory in small, distributed edge locations. Think of them as local courier hubs that are much closer to your consumers.
To maximize speed and resilience for a global audience, where should the original files actually be stored? A single regional bucket, even a really fast one, seems risky.
To maximize reach and minimize latency globally, the best practice is to store your files in multiple multi-regional cloud storage buckets. A multi-regional bucket distributes your content across vast geographic boundaries, ensuring that if one region fails, the origin is still available. More importantly, it allows the cloud CDN to fetch content from the nearest, most efficient origin location if the object isn't already cached, and then deliver it from the edge location that's closest to the end user.
That creates resilience and optimizes the origin retrieval time. But once the content is in the CDN, we want it to stay there as long as possible. We want a high cache hit ratio, which means the user request hits the already stored copy in the CDN, rather than the CDN having to reach all the way back to the origin bucket.
Improving the hit ratio is key to both performance and cost optimization. And our sources highlighted a very specific technical action here: customizing the cache keys. A common action is to improve performance by omitting the protocol HTTP or HTTPS from the cache key definition.
Why would the protocol matter for the cache key? If it's the same image, shouldn't it be the same key?
Well, the CDN typically generates a unique key for every object it stores. By default, sometimes this key includes aspects like the protocol. So if the default key distinguishes between https.example.com image.jpg and http.example.com image.jpg, then you end up with the exact same image stored twice in the cache under two different keys.
Which means if a user requests the HTTP version, it misses the cache entry for the HTTPS version, and that forces a trip all the way back to the origin.
Exactly. By telling the CDN to omit the protocol from the key, both HTTP and HTTPS requests are treated as the same object identity. They hit the same cached item, which drastically increases your cache hit ratio and therefore your delivery speed. It's a tiny configuration detail with a huge impact on global delivery efficiency.
This is where we bridge the gap between modern cloud architecture and the established enterprise data center. Hybrid connectivity is all about integrating cloud services with legacy systems, and the architectural choice here is entirely driven by business requirements for speed, reliability, and cost.
Right, the connectivity spectrum requires a really clear differentiation. We're talking about connecting your private cloud VPC to your physical on-premises network.
Yeah.
We have two main routes, the secure but variable public route and the guaranteed private route.
Let's start with the low-volume option, Cloud VPN.
Cloud VPN is the low-volume path. It's ideal for traffic volumes under, say, 500 ps. For use cases that aren't strictly mission-critical, where a quick setup is required and where cost-effectiveness is paramount, it's a secured, encrypted tunnel IPsec that travels over the public internet.
So Cloud VPN is like the secure postal van using the public highway. It's reliable, but it's subject to internet latency and potential variability that's outside of the cloud provider's direct control.
That is the trade-off. However, even with very low traffic, our source mentioned traffic as low as 200 kbps, if the business requires maximum high availability, or HA, you have to architect for redundancy. Even if you only need a trickle of data, if the system must be 99.99% available, a single tunnel is not going to cut it.
So what is the minimum requirement for 99.99% HA, regardless of the throughput?
You must deploy an HA Cloud VPN gateway, which by design provisions two separate redundant interfaces. You then have to connect those with two separate tunnels to your on-premises peer gateway. This ensures that if one tunnel fails, or if a specific cloud zone has an outage, traffic can instantly shift to the redundant tunnel, preserving that high availability guarantee.
That detail is critical. High availability is an architectural requirement, not a throughput requirement.
Exactly. And furthermore, you have to consider a multi-region deployment. If you have an application spanning two distant cloud regions, say US East and US West, that both need to talk back to your single physical data center, you must deploy a separate Cloud VPN gateway in each of those cloud regions. Each regional gateway must then have its own high availability tunnels connecting back to the on-premises peer gateway. You can't simplify that by relying on inter-VPC connectivity alone. That regional separation ensures localized ingress and resilience.
Okay, now let's contrast that with the high-performance option, dedicated interconnect.
This is the high-volume path. This is the private highway lane. This is for critical production applications that require guaranteed service level agreements, extremely high bandwidth, we're talking 20 Gbps, 50 Gbps, and even beyond, and a strict policy against ever traversing the public internet. It is a dedicated physical fiber connection established between your data center and the cloud provider's network location.
This offers guaranteed bandwidth and predictability because the traffic never once touches the public internet.
And achieving that top-tier SLA of 99.99% requires extensive physical redundancy. You need dedicated interconnect with redundant connections, often provisioned across two or more different metropolitan areas or availability zones, ensuring geographic isolation in case of a regional disaster.
We also saw a fascinating scenario combining high-volume ingestion needs. What if a company needs to move 900 terabytes of archived files, a huge one-time bulk load, but they also need to set up a permanent pipeline for daily incremental data ingestion?
You match the technology to the immediate need. For the initial 900 terabytes, the most efficient and cost-effective approach is often physical transport. Use a transfer appliance, a secure, ruggedized device from the cloud vendor. You load the data onto it on premises, and then you physically ship it to the cloud provider, bypassing weeks or months of network transfer time. Then, for the ongoing daily incremental data stream, you establish that high-speed, persistent, guaranteed link using dedicated interconnect.
That prevents the initial massive archive dump from crippling the network link that you need for your daily operational data, so a hybrid solution that involves physical logistics and permanent infrastructure.
And that intelligent layering leads directly to resilience and disaster recovery. The recommended DR procedures always emphasize layered redundancy, not just relying on a single top-tier connection.
What does that layering look like architecturally?
You provision your primary link with the highest performance option, like dedicated interconnect, because it meets your daily bandwidth needs. However, for a secondary failover option, your life raft in a disaster, you provision the less expensive flexible option like Cloud VPN. You then regularly verify your disaster recovery resilience by testing that failover path, ensuring that if the physical dedicated interconnect fails, your traffic can successfully switch to the Cloud VPN tunnels, maintaining connectivity just at a lower throughput.
That's a huge cost saver. You get the 99.99% performance guarantee daily through the interconnect, but you only pay the operational cost of the VPN for the emergency path, rather than paying for two fully redundant and very expensive interconnects.
It's the definition of smart, cost-effective resilience planning.
Okay, let's address the most common and most painful issue when integrating two large networks: hybrid network addressing challenges, specifically IP overlap. If both my VPC and my newly acquired company's data center use the exact same internal 10.10.0.016 IP range, what happens when I try to connect them?
You hit a fundamental routing conflict. The network has no idea whether a packet that's destined for 10.10.1.5 should go to the server in the VPC or the server in the data center. The general rule for migration is that the cloud IP range must never overlap with the on-premises IP range.
But in the real world, re-IPing a huge acquired network can take months or even years. If I need connectivity now, before that re-IPing is complete, what is the temporary but functional resolution strategy?
This is where we can leverage a powerful secondary use case for Cloud NAT. When you're connected to the overlapping networks via Cloud VPN, you configure Cloud NAT to perform NAT translation on that overlapping IP space. This means the IP addresses of the acquired network are dynamically translated into a non-overlapping range as the traffic crosses the VPN link.
So the NAT gateway acts as a temporary translator at the border, masking the conflicting IPs and allowing communication to proceed even though the internal addressing conflict still exists.
It's the architectural safety net that buys the networking team time to execute the full re-IP strategy. It solves the immediate routing conflict without requiring instant overhaul of the acquired environment.
Shifting now from on-premises connection to connecting two different cloud VPCs, we hit another potential IP challenge: connecting VPCs across organizations. I have two separate VPCs, maybe one for production, one for testing, or two different organizational projects that need to communicate privately.
The default ideal solution, the one that provides maximal throughput and minimal latency using the cloud provider's internal backbone, is VPC peering. It's fast, reliable, and it avoids the external gateway complexities of using VPNs.
And what's the absolute non-negotiable requirement for VPC peering?
That the two connected VPCs have IP ranges that do not overlap. If the addresses conflict, peering will fail because the routing decision just can't be made unambiguously.
So if I have overlapping IP ranges, which is a common occurrence across large organizations that were built without global coordination, VPC peering is just off the table. What's the definitive alternative?
That's when you must turn to Private Service Connect, or PSC. PSC is the required solution when two VPCs, even across organizations, have overlapping IP ranges, which makes VPC peering impossible. PSC allows the consumer VPC to access services that are hosted in the producer VPC, privately and securely. It abstracts the service access from the underlying network address space, solving that overlap problem architecturally.
It effectively separates the service from the network, so VPC peering connects the networks, but PSC allows private access to the service even if the networks themselves are fundamentally incompatible because of addressing conflicts.
A crucial distinction. And finally, in these hybrid environments, connectivity is useless if you can't find anything. We have to talk about hybrid DNS resolution.
Right. If I have a server on-premises and I'm connecting to a newly spun-up cloud VM, my on-premises server needs to be able to resolve that VM's internal cloud host name, something like vm1.c.my-project.internal. My local DNS server certainly won't know that record.
Exactly. You need a way to tell the on-premises server to ask the cloud's internal DNS system for those specific host names, and to do it securely over your private VPN or interconnect link.
What's the specific configuration element that enables this?
The Cloud DNS Inbound Server Policy. You configure this policy within Cloud DNS, and it specifically allows DNS requests that originate from your on-premises servers coming over that established private hybrid link to query and resolve internal cloud host names. If this policy is missing, your on-premises systems will fail to communicate with cloud resources using host names, forcing you to rely on brittle IP addresses. This completes the communication trifecta: routing, security, and naming.
As systems become massive, we move beyond simple network connection to advanced orchestration, especially in the world of microservices. This complexity brings us to the service mesh control plane, traffic director.
Microservices are great for agility, but they create a real management headache. You have hundreds of services, potentially spread across multiple cloud regions, and you need to manage granular traffic policies, like canary deployments or blue-green testing. You have to perform continuous health checks and enforce mutual TLS or MTLS for security between all those services.
And historically, managing all of that required manually configuring sidecar proxies right next to every single service instance, which just creates configuration drift and massive operational overhead.
Traffic Director is the answer to that. It's a fully managed control plane for the service mesh. So instead of manually configuring every sidecar proxy, Traffic Director centralizes the management of all those complex policies. It handles sophisticated traffic splitting, failure detection via health checks, and service-to-service security using MTLS, simplifying the entire orchestration layer for global, distributed applications.
It's the central brain that tells every individual piece of the microservice application exactly how to behave and communicate, ensuring consistency and resilience across the entire fleet.
It shifts that complexity from the application developer to the network management layer, which is where it belongs. It ensures consistency and allows developers to focus solely on their business logic.
Our final scenario today addresses a very specific, unique connectivity requirement for a single instance that needs to act as a hub. Custom network configuration for instances. Imagine a central logging server or a network appliance that absolutely must communicate directly and natively with instances in 2 or more separate VPCs, and we can't use peering or we have overlapping IPs.
This is multi-homing. You need that single instance to have a native internal present in multiple distinct networks at the same time. Relying on complex routing tables or VPNs just for a single instance to talk to 2 separate internal networks is, well, it's over-engineering.
So how do we give that single instance multiple native network presences?
The solution is to leverage physical, or in this case, virtual interfaces, multiple network interfaces, or NICs. You provision 2 or more NICs on that central compute engine instance. Each individual NIC is then configured to attach specifically to a different VPC and subnet combination.
So if my central server is in VPC 1 and I add a second NIC and attach that one to VPC 2, that server now has 2 distinct internal IP addresses and is natively reachable by all the other instances in both VPCs.
Precisely. It allows for direct, low-latency internal IP communication between that central instance and resources in 2 separate non-peered VPCs. This is a specialized but highly effective solution for things like internal monitoring hubs, centralized proxies, or high-throughput migration gateways that need to span multiple isolated network boundaries.
This deep dive has truly given us the architectural map, moving from the singular isolation of the VPC right up to the global orchestration of microservices.
We covered the foundational layers that are essential for any architect. The VPC as your isolated base, network tags as the source of dynamic identity for your security, and Cloud NAT as the essential secured, outbound-only gateway for your private instances.
And we clarified the critical differences in external connectivity L7 for application intelligence versus L4 pass-through for pure low-latency source IP preservation. And we detailed the architectural trade-offs between Cloud VPN for cost-effective, lower-volume hybrid connections versus dedicated interconnect for guaranteed high-volume resilience.
And critically, we addressed the organizational challenges. We differentiated between a local firewall rule and the high-level governance that's enforced by organization policy and shared VPCs. If you're just starting out in cloud networking, understanding these foundational distinctions will let you correctly assess the complexity of any architectural decision you face.
So what does this all mean for you, the learner? We've focused on the mechanics, the specific tools for specific jobs. You now understand that high availability isn't free. It requires 2 tunnels, even for a trickle of traffic. You know that IP overlap is a core technical challenge that requires specific tools like Cloud NAT or Private Service Connect to solve.
This knowledge is vital for building. But as we look forward, remember that connectivity itself is only half the battle. As your systems grow, as you scale from one VPC to potentially thousands of resources across a global footprint, the complexity shifts from connecting resources to governing them.
That raises a final provocative thought for you to explore. Knowing the power of centralized enforcement mechanisms like organization policy and the centralized network control of shared VPC, how would you design a management strategy today that guarantees network security standards across an entire enterprise? One that ensures thousands of resources comply, but without creating a bottleneck that slows down the speed and agility of your development teams.
That intersection of governance, speed, and security, that is the next frontier of network expertise. Mastering the fundamentals is step one. Achieving that compliant, agile scale is the necessary step two.
Excellent place to leave it. Thank you for joining us on the deep dive. We hope this gave you the critical insights needed to navigate the cloud network architecture with confidence.